All right, everyone, we see a question up on the board right now. It has three forces acting on this one object. We don't even know what the mass of that object is. Let's make it 20 kilograms. Doesn't matter. We want to find the net force that acts on that object. Well, we know that whenever we have multiple forces, we should draw a free body diagram. The good news is the free body diagram is already drawn for you on this question. We don't need to draw a free body diagram. It's already there. The next step is, until this point at least, it's been to say F net is equal to the sum of the forces. We're still going to do that. We're still going to say F net is equal to the sum of the forces here. But because there's two dimensions, it's not all on the x-axis and it's not all on the y-axis, so sum of both. It's not just as simple as doing F net is equal to the sum of the forces once. We have to do it twice for the x component and for the y component. But before we even get there, there's something there that we should respond to right away. Okay, there's a 30-degree angle. And what do we do? What do we say every time we see a funny angle like 30 degrees? We don't like funny angles. So let's get rid of it. Let's turn that 30-degree angle into something else. Okay, here's my 30 degrees up here. This is x. This is y. This is 10 newtons. Let's find the x component of that 10 newtons. Cosine 30 degrees is equal to x over 10. X is equal to 8.66 newtons. Sine 30 degrees is equal to y over 10. Y is equal to 5 newtons. So we've just effectively gotten rid of the 10 newtons. We can, if we wish, replace it with an 8.66 this way and a 5 newtons this way. We don't have to do that. You guys remember when we did adding displacement vectors together and adding velocity vectors together? It's the same thing, isn't it? It's really the same thing. Now is when we got to do the x and y components and say F net is equal to the sum of the forces. So let's say F net here is equal to F1 plus F2 plus F3. There are three forces. F1 is 20 newtons. What's F2? What's F2 for the x component? Yep, 0. Why is F2 0? Yep. Good. The 30 newtons is applied on the y-axis, straight down. Right, Devin? So we're going to say F2 is 0 newtons. What's the value of F3? 10, 5, or 8.66? It's negative 8.66. The 5 newtons is important, but not for the x component. Let's add those up. Okay, 20 plus 0 plus negative 8.66 is going to give me 11.34 newtons. Let's do the same thing for the y component here. We're going to say F net is equal to the sum of the forces again. F1 plus F2 plus F3. It's the value of F1 for the y component. We know this, right? How much of that 20 newtons is up or down? I see a couple people kind of doing this. They're afraid to talk, but they'll use their hands, hand signals. 0 newtons, it's 0 because it's acting to the right. None of it's up or down. All of it's to the right. And we're looking at the up and down here. F2 is, what, 30 newtons? F3 is 5 newtons? 5 newtons because that's the y component, right? And that's what we're concerned with here right now. Is that right? Is that right? What's wrong, Jazzy? Yeah, it should be negative 30 because it's acting downwards, right? Y component downwards. We add these up, by the way, guys, we get negative 25 newtons. Now what do? We get an F net, X component, F net, Y component. Now what do? This is all old physics 20. This is last unit now, right? All we're going to do now is say 11.34 this way, 25 newtons this way. We can find the hypotenuse, which is the resultant vector, the net force, by saying 11.34 squared plus 25 squared. And we can find the angle right here at the beginning of the diagram by saying the inverse tan function of opposite over adjacent, 25 over 11.34. What do we get for the force there? 27 newtons. And what do we get for the angle there? It's the inverse tan of 25 over 11.34. 66 degrees. 66 degrees south of west, right? Remember I told you back when we did displacement vectors that it was really important because you were going to see the whole vector component thing again this year, and you'd see it again in Physics 30 a few times. It's one of the most important concepts that carries over from unit to unit and from year to year, the whole idea of adding vectors together. This is just the same thing as adding displacement vectors, isn't it? If I said add 20 meters to the east, 30 meters to the south, and 10 meters at 30 degrees north of west, you guys would have done essentially the same thing. You would have got an answer of 27 meters for a displacement at 66 degrees south of west. So it's newtons instead. So what? Do it the same way. Jazzy? The question here would be, what's the net force? What's the net force? Now, we could also find the acceleration of this, right? How would you find the acceleration? You got the force. You want to find the acceleration. Yeah, Devin? Yeah, just switch out F net for m times A. So instead of solving for the net force here and the net force here, you would have said m times A and got the acceleration here, and got the acceleration here, and then do your vector diagram with acceleration instead, right? The alternative to that would have been get the net force the way we did, and then simply divide it by the mass and get the acceleration then. Either way works. Does that make sense? All right, so this is what we did last unit in terms of adding vectors, but it's also what we've done over the last couple weeks in adding forces together. It's just those two things combined. Okay, you guys could have done this question even if I hadn't shown it to you. Yeah. It should be south of east, shouldn't it? Is that what you were getting at? Yeah, you're absolutely right. Should be south of east. Okay. I like it when people point out my mistakes like that. What I don't like is that 26 people didn't point out my mistake. Only one person did. Listen, everybody makes mistakes, guys. I'm not going to be offended if you point out my mistake. I made a mistake once in 1978. It's been, what, 35 years, 36 years since I made a mistake? Hey, I make mistakes. Second mistake since 1978. Okay, don't be afraid to point out my mistakes, okay? All right, we had a little bit of homework questions. A little bit of homework last night to work on page 134, question 1 and 2. Question 2, we had a little bit of an issue in question number 2 with the direction here, but we drew that out for you, right? We said 300 degrees was like this. That was 300 degrees. And 30 degrees would have been like this. Are there any issues with question 1 or question 2? Or both? Any issues with that? Yep. 1? Okay. Is number 2 okay, guys, or do we need to go over that one as well? 2B? 2B? Or not 2B? That's really the question, isn't it? Yeah. So are you thinking of another question, or do you? Okay. All right. So number 1. So it says refer to example 3.3, which was this one. Suppose person A pulls a rope forming an angle of 40 degrees, B pulls with 20 degrees. So it's going to look like this. Here's the boat. Okay, here's 40 degrees. Here's 20 degrees. Each person applies a force of 60 newtons. We'll call that F1, 60 newtons. We'll call this F2, which is also 60 newtons. There's no friction, so that's it. We're looking at this from above, so there is gravity acting down, a normal force acting up, but since we're looking at it from above, it's pretty hard to draw those. Right? It's like looking at it from a plane in the sky. Okay. All right, so what do we do here? Well, first of all, we don't like funny angles, so we get rid of the 40 and the 20-degree angle. Let's draw these off to the side here. We got a 40-degree angle here with X and with Y with 60 newtons. Oops, there we go. Cosine 40 degrees is equal to X over 60. X ends up being equal to, what is that? You guys on this side of the room figure that one out, okay? Everybody on this side of the room figure out what X is. Okay, let's say sine 40 degrees is equal to Y over 60. Somebody on this side of the room, what's the Y component? Yep. Thank you. 38.56. Thank you, Ryan. On the left, on this side of the room, what's the X component? $45.96. 45.96. Thank you. Okay, let's do the other one, the one at 20 degrees now. This is X, this is Y, this is 60. Cosine 20 degrees is equal to X over 60. X is equal to, you guys on this side of the room, every single one of you is going to have an answer for this in 30 seconds. Okay, find X from here over. Okay, sine 20 degrees. You guys keep up with me over here because you're doing this one. Sine 20 degrees is equal to Y over 60. Okay, you guys find the value of Y. Every single person on this side of the room find the value of Y. Okay, what's X there? Okay, do you get the value of X there? 56.38 sounds reasonable. Thank you. Okay, you guys on this side of the room here. What is, Tyler, what's the value of Y there? 20.52, thank you. 20.52 newtons. Now, what we can do if we want is redraw this. F1 turns into 45 and 38. 45 to the right. And 38.56 up. We can redraw the second one, not as 60 newtons, but as 56 and 20. 56.38 to the right. And 20.5, is that 20.52, Tyler? Or 7? 20.52, thank you. Now we can add them up. Let's do our X and Y components here. Let's get rid of this, actually, so we got some space here. Let's say for the X component, F net is equal to the sum of the forces, F1 plus F2. F1 is 45. F2 is 56.38. We add those up, we're going to end up with 101.38. Let's do the Y component now. F net is equal to, once again, F1 plus F2. F1 is 38.56. F2 is 20.52. Is that right? Is that right? Should be a negative. Good. I don't count those mistakes because I made that one on purpose. That should be a negative because it's acting down, right? 38.56 subtract 20.52. That's going to give me, what is that, 18.04. Now we're going to combine them. It's positive 18.04. Let's combine them now. Just like we did back in our last unit here. We've got 101.38 to the right. and we've got 18.04 up this way. All of you guys right now, let's get the value of F, and let's get the value of theta there. I'll give you a second to do that if you don't already have it. All right, what's the answer to this, guys? The net force is, all right, we're going to use the Pythagorean theorem here. What do we end up getting? 103. We're going to round that to, how many digits should we have here? I'm not sure how much the question had. Was it 2 digits or 3 digits? 3. So we're going to say 103 newtons. And we're going to say the angle is, I'm going to guess on this one. I'm going to say 15 degrees. 10 degrees? 10 point. If we had 3 digits for force, we should have 3 digits for this as well. Is it exactly 10? 10.1? 10. Oh, sorry. So if you use the unrounded numbers here, it was exactly 10 degrees. Okay. 10.0, 10.1, whatever works out to be, guys. 10.1, 10.0, it would be 10 degrees north of 10 degrees north of east there. All right? Got it? Okay. I'll give you a chance to copy that out if you haven't already, and then we're going to give you one question for you to work on in class here, see what you can do with it. That pretty much wraps up the whole thing about forces here. All right, take a look at this one, please. Let's say that Kevin has, it's October, it's November, let's say. Yesterday was Halloween, the end of October. Kevin went door to door, like I do, with my son, to get as much candy as we possibly can. Kevin ends up with a bag of candy. It's full. It's a massive garbage pail of candy. It's full. It has a mass of 47 kilograms. Okay? It's almost as much as Kevin weighs, for heaven's sake. 47 kilograms. He likes candy. Okay? I don't particularly like candy. I just like the thrill of getting candy, free candy. Okay? 47 kilograms of candy. Now, let's say all of Kevin's friends see all this candy and say, I'd like to have that candy. Kevin's being a little bit greedy, doesn't want to share his candy. He says, no, you're going to have to take it from me over my dead body. So Kathleen punches him and then pulls it this way, pulls the candy this way. We're going to call that FK, the force of Kathleen, pulling with a force of 100 newtons. Jazzy says, well, I was a little scared to punch him the first time, but he's already kind of down, so I'll punch him now. Jazzy punches him, pulls as hard as he can, call it FJ there, with a force at 30 degrees, with a force of 50 newtons. Cade gives him a kick, now that he's down and crying a little bit, gives him a kick, pulls him as hard as he possibly can. Oh boy, he's a K too, isn't he? We'll pretend your name starts with a C, okay? Okay, Cade pulls as hard as he possibly can with a force of 30 newtons. Kevin holds onto this bag really, really tightly. He's not going to let it go. So when this bag gets pulled somewhere, when this bag moves, he's going with it. Hey, he's going with it. He's not letting anybody have this bag of candy. The question is, what is the acceleration of Kevin and his bag of candy? What is the not the force acting on Kevin and his bag of candy. What's the acceleration of Kevin and his bag of candy? We need an angle here, don't we? Let's make this 60 degrees. Okay, what's the acceleration of Kevin and his bag of candy? Kathleen's going to win this, right? But in the end, nobody else is letting go. Kevin's not letting go of his bag of candy. Jazzy's not letting go of Kevin. Cade's not letting go of Kevin either. I think Kathleen's going to end up winning, though. See what you can find for the acceleration here, guys. Okay, go ahead, Kevin. Well, yeah, that's a good question. Hey, that's a good question. Let's say that Kevin's unconscious on the floor now, and these guys steal his bag of candy, and they're pulling just the bag of candy. So Kevin's not going with it, okay? So we don't need to know what you weigh, Kevin, because you're not going with it, okay? So the 47-kilogram bag of candy, what's the acceleration of that bag of candy? Okay, do that right now. From start to finish, make sure you show all your work, make sure you show all your steps, including things like getting rid of these funny angles, okay? And then we'll take a look at it when you guys are finished.